Let's say I throw a ball at 30 meters per second up into the air. We know that g is about 10, so we can get our first vector very quickly. We also know, based on our starting conditions, that our velocity vector is going to start at 30 meters per second up. Our displacement vector will start at 0. We do have enough information to use one of our orange equations, but let's see if we can figure it out a different way. Let's try looking at a different orange equation. We can use our first orange equation to find out the velocity at the next second. How do we do that? Well, what if we turn everything in our orange equation into a vector? G is in terms of meters per second per second. So if we multiply by seconds, we will get meters per second, which looks like velocity. So we can multiply the vector g by the amount of time difference between our 2 points. Once we plug everything in, we can cancel out the seconds, and now we can add these two terms. Our new vector will be 20 meters per second going up. When we multiply our bottom scale by seconds, we get the same scale as we use for velocity. Because we are at a constant acceleration, every second we should see the velocity decrease by the same amount. So we figured out how to get our velocity vectors. What about displacement? This might be a little tricky, so just bear with me for a moment. You guys might remember the red equation. What if we only worked with the red equation over the course of 1 second? While we know that v is going to change over the course of that 1 second because it is not constant, the amount it changes might be so small that we can get a good approximation of x by just pretending it's constant. Let's basically start a new problem. Let's pretend that we threw the ball horizontally at the same v-naught we had earlier. We're going to ignore any acceleration for now. Let's pull out our red equation. Let's also do that same trick I did earlier of turning everything into vectors. Plugging in the given initial velocity, our time of 1 second, and our starting position of 0 meters, we get a final result of 30 meters. What if I told you that that 30 meters we just calculated is pretty close to what we would get for our original problem? Let's try double checking against our orange equations. Let's plug in our v0, the time elapsed, as well as our acceleration component. This gives us a delta x of 25 meters. This is close, but not exactly what we got using the other method. The earlier method is a good way to make approximations. We can make our approximation better by decreasing the time steps we take. Let's take a time difference of half a second. We've zoomed in to what's happening immediately between what happens at time equals 0 and time equals 1. Since we have a constant acceleration, our velocity will decrease half as much as it did in the gap between time equals 0 and time equals 1. Let's try our red equation again. This time, we'll use our initial velocity, 30 meters per second, and then a time of half a second. We plug and chug the numbers, and we get our displacement of about 15 meters. Now, let's use this displacement as our x0, and let's use the velocity at the halfway point. So we'll start with a velocity of 25 meters per second, we'll multiply it by the elapsed time of half a second between these 2 points, and then we'll add it to our initial displacement of 15 meters. We end up with a displacement of 27.5 meters. You can see that 27.5 is a lot better than the 30 we got earlier. By decreasing the amount of time between the points we check further and further, we can get better and better answers. If you want to see what happens when you decrease the space between points as much as possible, take a calculus class.